Lean Agile principle number 6, visualize and limit WIP, reduce batch sizes, and manage queue links. Boy, that's a set of powerful statements. Is that one principle or 4? Well, you tell me. We managed to fit it on a single line. Visualize and limit work in process. I'm going to tell you a story here, a true story about using WIP limits to help a team. So I went to a company in Chicago as a consultant, and this was serious business. People I know had invested a lot of money in this company, and they weren't doing great. So this wasn't here, and this wasn't here. They did have their storyboard. In other words, they had a visual storyboard of the work, and I was pleased by that rather than a task board. I'm not a fan of task boards because the completion of the task is not the goal. It's subservient to the goal of delivering the story. But they didn't have these dates, and they didn't have any indicator of where today was. So I asked somebody if they had a printer, and I printed the dates and placed them across the top. And then I said, does somebody have a rope or something? And nobody did. And I thought I was kind of a crazy man anyway. And they said, here's my headphones, they're broken. So I went and got those headphones and pinned them to the wall, and the cable went down, and it's right here. Now, here's the question for the reader. How is this team doing, and how do you know that? Look at it for a second. You can also tell when I was there. Wednesday, 2 p.m. All other things being equal, they're not doing very well. They're not going to land this sprint. They have 2 stories not started. They've got 5 in development. They've got 3 stories in test. They have only 1 accepted. They are 1 week in already to the process, and they have only 1, actually a week and a day into the system, and only 1 story's been accepted. This is not linear flow. This is not a flowing system. It's a sprint, but it's not a very good sprint. So let's do a thought experiment, and I'll tell you what we did there. What would be the effect of a 3-story work in process constraint on development and test? In other words, if we put a 3 up here and a 3 up here, what would happen? I'm going to leave you to think about that for just a minute. So put me on pause on this page and give it some thought. I'll finish this first. Here's your thought experiment. What would be the effect of a 3-story work in process constraint? And then this scenario. You're a developer. You just finished story 6. What would you do if there is no WIP constraint and if there's a 3-story WIP constraint is in place? So seriously, take a few minutes and give that some thought. Okay, now that you've done that, look at this again. So some crazy man, me in this case, came along and arbitrarily said 3 and 3. How does this thought experiment play out? I'm a developer and I just finished story 6. The crazy man, Dean, hadn't been here yet. What do? You know what I do. I go back and get story 11. Story 6 fits here. Story 11 gets started on, right? Gets in development. What have I done to the flow? Nothing. I've made it worse. I've actually increased the bottleneck. So we don't want to do that, right? So now the WIP limit is in place. It's 3. What does my developer do now? I wish you were here and I could look you in the eye. Most people say he or she needs to test. Fair enough, and that's exactly what I said. You know what that developer said to me? He said, I'm a Java guy. I don't really get HP Quality Center, and I don't generally test my own stuff, so I'm not really a good tester. So I don't know that that's going to help. Frankly, Dean, if you make me test, even on story 3, you've decreased my efficiency as a Java developer. You've decreased my value to the team. Did I increase his efficiency as a Java developer? Well, stories aren't going through the system, so I guess I'm not optimizing for more Java, am I? I'm not optimizing for more code. I'm optimizing for more tested code. So was he sub-optimized? Well, that's arguable. You could certainly see his perspective. But what were we optimizing for? We're optimizing for flow through the system. So even if this person is not as good a tester as some other tester, you've improved flow through the system. You've improved quality and yield because now all of a sudden you're in linear flow. So optimizing a component, optimizing for Jim, the developer, to create more Java code when I already have too much doesn't optimize the system. When you optimize the system, some components may be sub-optimized. When that happens, you achieve flow. And in that case, things go through the system much more quickly. Now, you might ask a question, how did that story work out, Dean? By the way, did they land this sprint? Because it's obviously too late to add WIP limits. The answer is yes, they did. When we came in, I think it was, I don't know if these dates were right, we came in on Tuesday or Wednesday, they landed the sprint with a source of pride, and they had spent the entire weekend, everyone, Saturday and Sunday, crunching away and working themselves, hard, and, ignoring their family's needs to make sure that that story got here. Did they land the sprint? No. They completed the work, but not with a sustainable pace and not with basically the ability to have a really clean, brain starting on the next sprint. So work in process limits change behavior, and therefore we need them and we apply them whenever we need to see that behavior changed. Now, it shouldn't be just a consultant dean coming along and saying you need WIP limits. This can be recognized by every team. So I mentioned earlier that our Scrum teams can apply work in process limits. They absolutely can. Reducing batch size is a separate thought, but an important thought. And this graphic is an awfully important graphic here in the middle. And this is from Poppendiek's work. Excellent writings, by the way. Poppendiek's books are very readable. Very early thinkers. I think 2001, 2002, thinking about lean software development. They should stand proud of their work, as well as Reinertsen. A decade later, he was writing at the same time earlier, but in kind of a slightly different area. Here's a chart that they maintain that says basically, here's the impact of batch size on yield variation in yield and cycle time, right? So this is cycle time, this is utilization. So let's just say that we're running about 60% utilization. And a big batch and a small batch don't really matter. They're all going to come out with a pretty reliable cycle time, and I can predict it. But let's move over here. Let's move to 100% utilization. And what did Reinertsen say earlier? 100% utilization basically is an economic disaster. Why? Okay, because if I put a big batch in 100% utilization, I have an extremely high variation in cycle time. What's that mean? It means you're late, okay? Cycle time is almost too nice a word. We did not deliver. We delivered really late. So as utilization goes up and batch size goes up, we get essentially later and later. Well, what are we going to do about that? Well, we have to think deep thoughts about how to handle that problem. And we need to reduce those batch sizes, because the smaller batch sizes, we're going to run at high utilization. It's pretty hard not to do that, right? We're not going to have half of our developers sitting there waiting in case something goes wrong. But look what happens with a small batch. We can run at high utilization and still have a pretty reliable outcome. So large batch sizes hurt us. They increase variability. High utilization increases variability. Severe project slippage is the most likely result. Aha, root cause. If I can ask 100 large programs, what is utilization of your program? And they'll typically say this. Actually, you managers already know they say more than that. We're overtasked. We're running a waterfall process. I'll indicate that up here. What's the batch size for the project? The entire requirement specification. So what's your batch size? The biggest batch size imaginable. So I take the biggest batch size imaginable here, and I drive it into a system that's running at 100% utilization, and what I get a really terrible answer. So if we're going, company to company, industry to industry, building big systems and saying, why can't we deliver on time? It's because we're running at too high utilizations for our batch size. We need to reduce batch size. So what the math tells us is that if you have a large batch and a highly utilized system, okay, a whole bunch of people want to get to the Denver Broncos game, okay? And the road is fully utilized, that with that batch size and that level of utilization, some people are going to get there just fine and other people are going to miss the whole darn game because the freeways are going to become overloaded. This is predictive. This is programmatic. This is expected. You should expect it. If you're running high utilizations and big batches, that's the result you're going to get. So obviously, not a great plan. Most important batch is the transport, the handoff batch. Okay, what's a handoff batch? Well, we talked earlier about it could just be, here's a big batch of requirements, and I hand those off to design. That's a handoff. What do I get all this code done and I have a group of 300 testers in India? That is a giant handoff batch, right? So the bigger that batch is, the same result's going to happen. Reflect back on our customer. They're my customer. I give them a giant batch. What do you think their utilization is? You think they're idling over there? Absolutely not. So the most important batch is the handoff batch, which means we need to divide our work up. Remember the requirements of design, we need to go get a little tiny piece of that. We need to run that through the system because then it's a really small batch here, it's a small batch here, it's a small batch throughout the system. Co-location enables small batch size. You hear so much about agile teams are co-located, and boy, they largely are, but they're not always. Why do we co-locate them? Just 'cause it's fun? It'd be fun if they were closer together. No, because it encourages communication and their batch size is much smaller. I'm a product owner and I need to talk to my team. They're on the 5th floor of the building on the Microsoft campus. I'm on 4 buildings away. If I want to have an efficient conversation with those guys, I'm here and they're there. Here's my team. So if they're there and I have some things to talk about and I have to ride over there on my scooter, probably in the rain, to talk to them, I need to take a lot of things. I need a lot of things in my bag because then when I process those, I can be very efficient. I'm here, I rode over on my scooter, I can process 5 things. Instead, what if the same situation occurred here, but I'm right here, okay? How many things do I need now to talk about efficiently? I could do it with 1. My batch size could be exactly 1 thing. We just had 1 discussion. Hey, Jim, what do you think about foo? Versus blah, blah, blah. Hey, Jim, blah, 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 blah. So co-location is a facilitator for small batch sizes. Small batch sizes is a facilitator for improved cycle times, even in the presence of high variation. Reduce batch size. Now, you probably weren't thinking about batch size before you got to this course, but you are now. And I want you to continue to think about it because there's additional impacts. Large batches also create more work in process, right? Big bunch of stories are going to tend to process those sequentially. And lastly, good infrastructure enables small batches like we talked about with test and test automation. Now here's a fun exercise for you. We're not going to do this here, obviously, because I can't be a group of 5 people. Here's the instructions. Get together with your team. Take 10 pennies. 1 person is the timekeeper. The remaining 4 people process the coins. Process them as follows. Person by person, flip all coins 1 at a time. By the way, recording your own results as you go, heads or tails. The person that flips records. Pass all coins at the same time to the next person. The timekeeper records the time from the start of the first flip to the completion of the last flip. In other words, how many minutes does it take? And I'll give you a hint. It's probably a couple minutes. So run that experiment. Then say, okay, record that result. Record your time. Then run a different experiment. Similar process. Now, each person flips each coin 1 coin at a time and records the results. And when he or she is done, they pass the coin to the next person who repeats that process. The timekeeper records the time from the start of the first flip to the completion of the last flip. It's pretty unlikely that you're sitting around with a group of people that can do this, so I'm going to leave you to that as an experiment. But let me go to the whiteboard and let me show you the results of doing this experiment again and again with quite a group of people. So let's do that now. Clearly, if you're viewing this course, you probably don't have 4 people to sit around flipping pennies with, but I like to use this exercise a lot. I use this and the ABC, the 3 project exercise, most frequently. One time I had 45 minutes total with a group of C-level executives who were contemplating this move, and I had to think about, do I want to hit them with some PowerPoint slides and numb them out like some vendor of some solution? I'm really trying to get into their brain and get them to think a little differently about the project. So I pulled out my ABC and my pennies and a couple of slides on lean, and that was my full 45 minutes. So I actually had these executives flipping pennies at the conference table. Maybe they thought I was a little zany, maybe not. But in any case, getting involved, kinesthetic, learning by experiencing is a good way to go. So don't be afraid of these kind of silly, simple tricks. Executives are people like you, like me. I guess I'm one, and I don't mind learning something with my hands. Sometimes it's easier than just listening and trying to absorb. So we typically have a pretty good group here, maybe 4, 5, 6, 7 tables. They run the experiment, it goes like this. We run the first one, the batch of 10 pennies first, and the data starts coming in. And you start seeing things like 2 minutes and 24 seconds, 3 minutes and 9 seconds, 1 minute and 50 seconds, 140. Sometimes there's an outlier, 130, something like that. 2:53 and 3:45. Now we look at the data and say, wow, look at that. From a minute 40 to 3:45, exactly the same instructions we're giving to people in the same language. Their working environment is the same. It's not like they're working at different platforms. They're sitting at similar tables. They were instructed exactly the same way. What does it mean? It means that there's a fair amount of variability here, pretty high variability in that batch size. So passing 10 pennies around a room, flipping and just counting heads or tails, you'd think that'd be pretty steady state, right? You think you could predict that, but it's not. It's pretty variable. And they're surprised by that. And they talk about, well, the instructions weren't clear, or over here we dropped a couple pennies. That's because there's a lot of variability in a big batch like that, right? Maybe somebody got a coin that didn't have a head or tail on it. Who knows exactly, but the results are kind of all over the map. Pretty shocking, really. So, okay, let's run the second half of the experiment. Let's go down to a batch size of 1. So when you flip a penny, you record the result, you hand it to the person next to you. Depending on how you feel about your personal space, maybe they can pull that penny, make a little joke about that, into their working area and move very quickly. And it goes very fast. It comes out entirely different. It's about a minute 20, minute 30, right? Minute 45, a minute 15, minute, well, you get the idea. We'll just pretend like it's a minute throughout. Way different. So same people, same environment, slightly different experiment. We fire off a different process and we get an entirely different result. So the 10 pennies got to the 10th station twice as fast. That's interesting. We got the same work done twice as fast with a much higher degree of predictability. Small batches go through the system faster with higher predictability. Fundamental tenet of lean and product development flow. But one more thing. So imagine 4 people sitting here. I asked the question, in experiment number 1, which of you were in station 4? Now every table, somebody has to raise their hand, and if they don't, then I really have a challenge at that point. It's like, well, okay, well, wait a minute, did you do the experiment or not? So those people raise their hand. I say, if you were in station number 4, raise your hand. And they raise their hand, and I say, now you know what a tester's life is like in a waterfall project. And typically there's a few chuckles, because you're sitting there waiting. The clock started, right? The pennies are over here. I'm here. A bunch of pennies headed my way. The clock is ticking. Tick tock, tick tock, tick tock. They're moving my way. I can't do anything until the pennies get to me. That's obviously pretty silly to have some test capability, maybe somebody doing automated tests, sitting and waiting for some work that isn't there yet. So what do we do as management? We don't have those people there. We have them working someplace else. So what happens when the pennies get there? We bring them in, add them to the team, start testing. They have no context whatever. They haven't seen any of the pennies before. They haven't seen the process. They haven't seen these new user stories or these new features. And we're asking them to quickly assure that the quality is in the system. That seems like a terrible plan. Let's serialize the work. Let's get stories moving through the system faster. Let's get features and capabilities having a linear flow through the system and keep everybody engaged. And just the experience of sitting there and doing nothing while waiting for a big batch to come your way is pretty visceral. People kind of understand that. They go, that wasn't very comfortable, versus the second part of the exercise where everybody is involved almost immediately. That's what it's like being on an agile team. Everybody is involved. Stories are moving very quickly. I'm going to be testing this one today, this one tomorrow. Same goes at the program level. Features are moving through the system. We're all actively engaged and involved. Nobody's waiting for a big batch to come land on their desk. What did we learn? We learned that large batches go through the system with far less predictability. It takes a lot longer to essentially the same amount of processing work. Now, optimum batch size is an example of what's called a U-curve optimization. And a U-curve optimization is a thing that basically says there's no one right answer. There's a range of answers. There's no singularity that says your items per batch could be 10 or 1. Right? 1 worked better for you? Well, maybe 2 would have worked even better. You don't know, because we didn't run the experiment. Okay? But what we see is that our total cost, when we think about batch size, is a function of 2 costs. One is the holding cost, and that tends to go up with the larger items per batch. So imagine I've got 200 pennies, or 200 combines, or 200 fenders. Well, the more they have, the higher my holding cost, right? Inventory carrying costs, they're chewing up a bunch of space on the floor, etc. Okay? That cost goes up. Transaction cost, however, total transaction cost can go down because I don't have very many transactions. I have 100 fenders, so I don't have to kit them very often. So I have my total cost, the cost I care about, is the sum of the holding cost for a batch of any size, just take that size here, and the transaction cost. Well, I want my batch size to go smaller. I want to go that way, right? How do I do that? I have to lower one of my costs. I have to lower them both. So the total costs are the sum of holding and transaction costs. Higher transaction costs shift optimum batch size higher. So the higher this is, the higher the transaction cost, the higher the optimum batch size needs to be. So what do? Higher holding costs shift batch size lower. So what do I need to do? Let's just take a look. If I can reduce the transaction cost, let's look at the difference here. One has the same holding cost and a different transaction cost. So now we need a real example. So let's say that it's my dev and ops again, right? And I have a big batch of software, right? Lots and lots of new user stories. And the transaction cost is every single batch requires validation. I have a 300-page run book before I deploy software. I have to do database migrations. I have to do validation of the potential to reverse the change. I've got lots of security protocols that need to go through. I can't deploy that to my 1 million users, okay, until I've run my run book. That's expensive. Well, what if I could cut that time in half somehow? What if I automated all of that stuff so I could get faster feedback? Well, that would lower my transaction cost, right? Because now it doesn't take nearly as much. When I lower my transaction cost, I move the curve such that my items per batch is smaller. So if I want to get more efficient, I want to lower my total cost of moving stuff through the system. Affecting the transaction cost is a good way to do that. And we're mostly struggling with those handoffs. So if I can make it easier to communicate with my tester or the test team, if that's the way we're structured, or easier to communicate with DevOps, I can lower the cost and I can lower my batch size. And lowering the batch size lowers cost and it also increases predictability. So if you want high predictability and low cost, think about batch size. And when I reduce batch size, I get higher predictability. Things go through the system more predictable. I get faster feedback. I reduce rework. It lowers my overall cost, and it probably saves twice what you think. So as we think about these transaction costs that increase cost of delay and these handoffs, and we think about our verticalization of work, and we think that we have an SRS or a set of code that hasn't been tested or a set of tested code that hasn't been deployed, we need to think about lowering the transaction costs so that we can lower our total cost and become more reliable. And becoming more reliable at lower cost, seems like an oxymoron. And the reality is easy to do if you focus on batch size. Queue lengths. Well, what's a queue length got to do with anything? Well, it has a lot to do with a lot. Number one, we all hate queues, right? This was an actual email I got from, I sent an invoice to one of my customers, and they said, "Thank you for contacting us. We're experiencing increasing volume." So for that customer, it was easier for them to program a server to say you're not really going to get service than to provide the actual service. Well, that's not particularly helpful, okay? Have you ever seen a queue you liked? Well, there are some exceptions, I won't go into them, but queues have longer cycle times, increased risk, increased more variability, lower quality, and frankly, less motivation to complete the work. Let me just pick variability for a second. Let me pick this one and focus on this one. So let me give you a true story. It's both an analogy and a true story. So let's say that there's a Starbucks next to a gigantic enterprise building. Pretend like that's a big enterprise with all kinds of little windows and stuff I can't draw here. And there's a Starbucks, and here's me. And I'm going to this enterprise, and I'm going to, let's say, run a release planning session, a PI planning session. And they start early because it's a distributed environment. We'll see later more from this vignette. So they start fairly early. We're going to, let's say, start 7:30 US time. And there's 100 people in the room. Okay, cool. And I'm going to facilitate this. Well, that's going to be a pretty big job. I'm going to need my fix before I do that. So I go to Starbucks. So let's just look at what happens at Starbucks. Let's just say that there's 3 people in the queue, and I come in and I need to get my fix so that I can get back to my enterprise. 3 people in the queue, no big deal. This guy orders a venti latte, this guy orders a flat white, and this guy orders a heated bagel with an extra hot soy latte, okay? No big deal. But now let's say there's all these people in the queue. Whether or not I'm on time now depends on what they order. If they all order a venti latte, I'm fine. I'll make my meeting on time. But if they all order a bagel, I'm going to be late, and I don't control that. So the longer the queue, the more variability, the less control I have over that. Increased risk, what's the risk to Starbucks? Well, they're pretty clever guys. I might leave. I might step outside and say, I don't get my coffee today. It costs, so they miss my $4. Longer cycle times, that's obvious because I can't get, I can't serve these people. A lower quality, well, let's put it that in the requirements perspective. Here's my stack of requirements. Okay, it's a really, really big batch. What's the probability by that time that batch is fully processed that they're all still good? Well, somebody rotted. One of them rotted away in the meantime. Less motivation. Okay, I used to do an experiment in class. Say, identify the top 3 things on your to-do list. And they would do that. Identify the top 20. Okay, they would do that. Which is more motivational? I can think about 3, 20, that's just depressing. Okay, so long queues. I have a huge amount of software that I need to test. Nah, I think I'll go home. Oh, I only have 3 more user stories. I can get those done before the end of the day. Long queues, all bad. Nothing good about them. And we have them. We don't necessarily see them because we're not at Starbucks, but they're still there. That big fat software requirement specification is a giant queue, okay? And we know some things about queue lengths as we'll see. What we know about queue lengths is they behave very well. They behave exactly the same. They behave in accordance to this thing called Little's Law. And it looks kind of funky because we've used algebraic symbols to express it here, but it basically says the average wait time for an item in the queue, right? So here's my queue, is equal to the average length of the queue divided by the processing rate. That makes sense, right? Here's my item in the queue. Here's a bunch of folks ahead of me, and they're getting venti lattes, so that's the average. But maybe they're getting venti lattes and other things. The average wait time is equal to the average length of the queue divided by lambda, the processing rate. Okay? That's just true. It does meet your natural instinct, right? The longer the queue at Starbucks, I'm probably going to wait longer. And by the way, if they have 2 people serving coffee, I'm going to get done twice as fast because that increases the processing rate. Totally sensible stuff, okay? So we need to understand that law, and we need to recognize that, yes, a faster processing time decreases wait, for sure. If they could pour coffee faster, I could get my coffee fix faster. But if you really want to be fast, you need to control queue lengths. And exactly that experiment is actually a different Starbucks. I watched a Starbucks queue, and I was timing using my iPhone. I was trying to time this. I was trying to figure out what this average was because I was really trying to understand Little's Law. Because even though it's intuitive, I kind of wanted to make sure I really got it. And I watched them, and as soon as it got to about 10 or 12 people, another barista would magically appear from the back. Starbucks understands queuing theory, okay? They control the wait times by controlling queue lengths. They can't pour coffee faster, they have to provide more people to do lambda. So how does this work in our world? We're not a Starbucks, so you're going, maybe you're bored with that, and you're going, well, that's kind of stupid. It's great if I was a Starbucks, but it works exactly the same. So let's just say that my team can deliver 10 features per quarter, and we've committed 30 new features. Okay, 30 items, 10 per quarter, it's a 3-quarter wait. That wasn't quite as fast as I thought. I thought we were going pretty fast. What if it was twice that? What if it was 60 items? How long do I wait now? 1.5 years. And the only difference was the items in the queue. Now, we're going to talk more about queuing theory. We're going to talk about backlogs. And the thought experiment I'd like to leave in your mind is when is a backlog a queue? They don't behave exactly the same, but they can have some of the same characteristics.